Now we have discussion about single sideband modulation here. To understand the SSB, first of all, we need to know what is the Hilbert transform. So here you see that how we are able to obtain the 90-degree phase shift. On the basis of that, we have Hilbert transform pair, and later we'll see what is the single sideband suppressed carrier and how we are going to obtain the time domain as well as frequency domain representation. So this is one of the important question. Okay, about if the question is going, they're asking about represent the SSB-SC in time domain and frequency domain. Apart from this, we have Hilbert transform also separate question. So still you didn't subscribe our channel, please subscribe, share and like, write your comments. Okay. So now we have, first of all, Hilbert transform. So already you are aware about the Fourier transform. So what is use of the Fourier transform? So there you are going to represent from the time domain into the frequency domain, and you are trying to find the what is the energy content of the signal. So that is the main basis on which we are able to separate the signals. So that is the parameter is what the frequency. And another thing on which we can separate this signal is the phase selectivity. Like we'll say that somebody is leading by 90-degree, lagging by 90-degree, or leading by 180-degree, like this discussion is there. So one of the thing is that in phase shift, we can obtain the 180-degree phase shift. But to obtain this 180-degree phase shift, we require an ideal transformer. So maybe it's not always possible to obtain the ideal transformer. So in place of that, we are going for the plus minus 90-degree phase shift. So here signal is being shifted either by the plus 90-degree or minus 90-degree. Then resulting function will have time domain representation. That time domain representation with 90-degree phase shift is called as the Hilbert transform. So what is the, suppose short question, what is Hilbert transform? So Hilbert transform is what? It is the time domain representation of the signal with plus minus 90-degree phase shift. So now here we are trying to obtain that Hilbert transform pair. So like some signal is taken as the g of t, and for that if you are trying to represent in Fourier transform, so that you know that that value is capital G of f. Whereas the Hilbert transform of this signal g of t will be denoted by g cap of t. So how we are going to define g cap of t? It is 1 by pi integration over minus infinity to plus infinity of g of tau by t minus tau into d tau. So here g of tau is the function, and in the denominator we have t minus tau. Okay. So it have so if you see that it is the linear operation, as well as we have Hilbert transform, that inverse we can obtain. So like here we have g cap of t, so that if you obtain the inverse of this, we'll get the g of t. So in case of inverse, we have g of t equal to minus 1 by pi integration minus infinity to plus infinity. Here in place of g of tau, we have g cap of tau and t minus tau d tau. So here this function has changed since we are obtaining the inverse Hilbert transform of g cap of t. That's why here we have g cap of tau, and outside here it is multiplied by the minus sign. So this two is called as the Hilbert transform pair. So might question will be there, write the Hilbert transform pair expression. So this g cap of t and g of t you need to write. And this Hilbert transform can also be represented with the help of convolution. So you have idea about convolution. Okay. So how will represent g cap of t with the help of convolution? So it is being multiplied by the 1 by pi t. And already you are aware of the definition of the convolution theorem. Okay. So now finally, we are going to define what is 1 by pi t. So that can be minus j signum function. Okay. So this can be from minus j signum function can be written as 1 by pi t, or 1 by pi t can be written as the minus j signum function. So first of all, we need to understand what is the signum function. So it is the function which having value as the 1 for the positive frequency and 0 for the negative frequency, 0 for the when frequency is 0 and negative when the frequency is negative. So this signum function might you can see, okay, for the positive frequency, its value is what here? +1. For the negative frequency, its value is what? -1. And for this f equal to 0, this frequency, that value is what here? 0. So here this part f is greater than 0. This part f is less than 0. Here f equal to 0. And this is the amplitude. So this is how we are able to define the signum function. So again, it is the objective question. Define the signum function or write the expression. So now we are going to see the relation between the Fourier transform as well as Hilbert transform. Okay. So that g of t Fourier transform, what we can write? If you have function g of t, so that Fourier transform we are writing as the capital G of f. And now here we have g cap of t. So its Fourier transform will be written as g cap of f. Okay, so that is written here. G cap of f is the Fourier transform of the g cap of t. So which is defined as minus j signum of f into gf. And signum function already we have seen. And this portion is what equal to 1 by pi t. So now we obtain the Hilbert transform, that is g of cap of t by, if you are going to pass this signal g of t through the linear two-port device and which having frequency response equal to minus j signum of f. Okay. So this signal g of t is going to pass through the two-port network. That transfer function what we have, frequency response minus j signum of f. And this device is able to produce the phase shift of -90° when for the positive frequency and +90° for the negative frequency. So be careful. For -90 means positive frequency is there. Okay. And when we have +90° phase shift, so there we have negative frequency. So this part you can see here. Okay. For the negative frequency. Okay, so what we have? Positive values, and for the positive frequency, what we have? Negative value. So this is the phase characteristics of that linear two-port device through which that g of t is going to pass. So finally, what is the basic properties here? So this signal both g of t and g cap of t having a same magnitude spectrum. And g cap of t is the Hilbert transform of g of t, and Hilbert transform of g cap of t is the minus g of t. That already we have seen in the expression. And signal g of t and its Hilbert transform g cap of t are both are orthogonal over the entire time interval. So orthogonal, you know about that, okay? So orthogonal, like we have OFDM, orthogonal frequency division multiplexing. So these all are the 90° of each other. Okay, so finally we have in integration of g of t and g cap of t, both are the Hilbert transform pair. So that product integration over the minus infinity to plus infinity is going to become equal to 0. These are the basic properties. Now finally we are going to see what is the requirement of SSB-SC. Why single sideband is required. Okay, so you have seen in case of amplitude modulation, we are going to transmit the both sidebands along with carrier. So that we are overcome in DSB-SC. DSB-SC is what? Double sideband suppressed carrier. So for this already separate lecture is available. All generation, detection, everything is methods are explained. So in this both case, if you compare AM and DSB-SC, so in case of AM, what we have? Upper sideband, lower sideband, carrier is there. In case of DSB-SC, upper sideband and lower sideband is there. So in both cases, we have wastage of the bandwidth. Since upper sideband can be obtained from the lower sideband or lower sideband can be obtained from the upper sideband since both are symmetrical of each other. So this we need to save the bandwidth. Okay, so that we are able to obtain that characteristics by using the single sideband. So single sideband means either lower sideband or upper sideband will be transmitted. On the basis of that, we can determine the another sideband. Okay, so now we are going to see that SSB in the frequency domain as well as time domain. So here, this message signal or baseband signal is considered as the m of t, and its Fourier transform will be m of f, and it is band limited in the range of minus w to plus w. So now this already we have seen that in case of DSB-SC, modulated wave is obtained by multiplying the message signal with the carrier signal. So here carrier signal is considered as the AC cos 2 pi FCT. So in case of SSB, that upper sideband is what? The frequency which is above the carrier frequency FC. So that is for the positive frequency, and it is the frequency below minus FC in case of negative frequency. So since when we're talking about the spectrum that you have seen, and it will be much clearer in the next diagram. So now here we have bandwidth requirement is only equal to message bandwidth, not required the twice of the message bandwidth. Okay. So what is the advantage here? It's eliminate the high power carrier and reduce the bandwidth. Both benefits we are going to obtain here. In case of DSB-SC, we are able to save the power, and now in single sideband, we are able to save the bandwidth also. So that is the double advantage here. But a disadvantage is what? It has a highly cost and more complex. But somewhere, something you are going to obtain means some sacrifice you have to do. So here if you see that different spectrum, this is for the message signal, what we call baseband signal. Then we have DSB-SC. So minus FC, this side upper sideband. Here we have upper sideband, this portion, and right side lower sideband. Here, this is going to give us lower sideband, this side upper sideband. Okay. So that is already in case of DSB-SC. So here you are seeing that bandwidth requirement is extra. Whereas in case of single sideband, either we are able to transfer the that is either upper sideband or lower sideband. So in this diagram, upper sideband is shown for the negative frequency as well as positive frequency. So for this duration only we have information, and from minus FC to plus FC it is 0. Okay. Again from the FC, after that we have upper sideband, and after FC plus W again it is 0. Okay. So now in case of LSB also, we have this information between minus FC to minus FC plus W. Again, it is 0. Again, from the FC minus W to FC, and right side again is going to be 0. So this is the spectrum. So a spectrum representation is called as the frequency domain representation. Now we are going to see in the time domain. So here time domain is important in case of SSB-SC. If you see, really we are going to see how we'll obtain the LSB or USB that we are going to see here. So to explain this time domain concept, it is important to know the Hilbert transform. So that's why already we have seen that what is the Hilbert transform, that having plus minus 90-degree phase shift. And SSB-SC signal is what? Band pass signals or band limited signals. So it can be represented in the canonical form. So that having in-phase component as well as quadrature components. So modulated wave in case of SSB-SC can be written as SI of t cos 2 pi FCT minus SQ of t sin 2 pi FCT, where SI of t is the in-phase component, SQ of t is the quadrature components. And both components are obtained by using how we have product modulator as well as low pass filters, like we have what we are seeing here. We have like in case of DSB-SC, how we are going to obtain the product of message and carrier. Similar concept is there. So now if you see that frequency transform of the in-phase component, that is S of F minus FC plus S of F plus Fc, okay, in the band of minus W to plus W, and remaining portion it is 0. Similarly, in the quadrature, component is here, J is outside, so it is imaginary parts, S of F minus Fc minus S of F plus Fc. So here if you see that sign is minus, here sign is what? Plus. So it is also in the range of minus W to W, otherwise it is going to be 0. So this one here we see that by S of F, how we are going to obtain S of F minus Fc as well as S of F plus Fc. So this is the spectrum for the upper sideband. Just now we have seen. Now you are going to shift this one. Okay, so here function is what? Inside the function S of F minus Fc. So from the signal system already you know. So when it is function is going to shift, it is the minus here. So that is shift will takes place right side. It will have plus, then shift will be left side. So here what we have? Minus Fc. So that's why, like suppose in case of time domain also, if you're talking S of t minus b, so this is going to shift right side. If you're talking about S of t plus b, it is going to shift where? Left side. So here what we have? Minus. So it is going to shift right side. So you are saying that this entire signal is shifted here, right side. So we have here plus Fc is being added here. It is minus Fc, so plus Fc is added. So now what will happen here? This part become, if you add here plus Fc, so this becomes 0. Again here plus Fc, so this becomes 0. So this is the first one is not 0. First one what we have? Minus W. Minus Fc minus W plus Fc. What will get? Minus W. So that's why this is shifted to minus W here, and this portion is shifted to the 0. And if you see this part, here you are adding plus Fc, again plus Fc. So this is going to be 2Fc, and this one is the 2Fc plus W. That is how it is being shifted. And this shows that it is continuous, but the space will be less. So that is showing the folded one. And whereas if you see in case of S of F plus Fc, so it is going to shift left. So we are doing the minus Fc here. So now we have minus 2Fc minus W, minus 2Fc this part, and similarly right part is shifted to the left one. So we have here between the 0 to W. So now you have seen that how shifting takes place. So in phase components is what? Combination of both. Okay. In phase just now we have seen. So what we have? These both are being added together. So now if you are going to add both signals here, so what will happen? This portion and this portion are this symmetric, so it is being cancelled. Okay. And only, or you can say that it is not on the basis of symmetric. So that signal is not defined actually in that range. So automatic that will become 0 for us. Okay. And we need the signal only in the range of minus W to plus W. So minus W to 0, we have this portion. Okay. And again 0 to W, what we have? This portion. So finally, this is going to be the in phase components. Okay. So already we have defined in phase component where in the range of minus W to plus W. So for the minus W to 0, this one, and 0 to W, this one, that is in phase components. So similarly, quadrature components, that is also same combination of this, but what is there? Minus sign is there. So minus sign, due to this minus sign, this part is being inverted. So that we are getting this portion. Okay, due to what is the quadrature component, here sign is minus. J is there means it will be along the y-axis, that you know about the imaginary parts. So this portion is due to S of F minus Fc, and this portion is due to S of F plus Fc, and here sign is minus, so it is inverted one. So now you can see that quadrature components. So now finally this in phase components we can define, that is the what we are getting, half AC M of F, okay, in phase components, and M of it, what is this? This is the Fourier transform of message signal. So in phase component, finally we can write in time domain as Si of t 1 by 2 AC M of t. So M of F is the Fourier transform. So Fourier inverse is the time domain. So we have m of t here. This is the equation 5. So now equation 5 become important for us, that we are going to substitute in the equation 1, where we have Si of t cos 2 pi f ct minus Sq of t cos 2 pi f ct. So now we'll talk about the quadrature component parts. So you are seeing that for the positive frequency, this is the value. For the negative frequency, we have this value. So that we are writing from where? From this graph. So finally, here this equation 6, that is the quadrature components. Here we are going to use the Hilbert transform. So SQ of can be written as minus j AC by 2 signum function and m of f. So signum already we have seen. It values 1 for the positive frequency, minus 1 for the negative frequency, and it is 0 for the f equal to 0. Okay. So this quantity, what is in the RHS minus j signum of f, m of f is what? It is the Fourier transform of the Hilbert transform of the m of t, that is what? M cap of t. So this is the Fourier transform of what? M cap of t. So please go through the Hilbert transform seriously. So finally, SQ of will be written as AC by 2 M cap of f. So now if you take the inverse, Fourier inverse transform of this equation 9, so we'll have time domain representation. So that is SQ of t equal to AC by 2 M cap of t. Okay. So now we got what? In-phase component and quadrature components. So any doubt is there, you can write in the comment box. So now finally this equation 5 and 10 we are going to utilize where? In equation 1. Okay. So there we have, if you see that equation 1, we have written there Si of t into cos 2 pi fc t minus Sq of t, and here we have sin 2 pi fct. It has phase shift of the 90 degrees. So one is cos, another is the 9 here. So finally we have substituted the value of Si of t, that is Sc by 2 m of t, and Sq of t is the half AC by 2 in, that is half AC m cap of t. So that value is substituted, equation 5 and 10. So now this is going to represent the upper sideband. Here sign is minus, is going to represent the upper sideband. So in a similar discussion, if you consider the, and if your sign is positive, it's going to represent the lower sideband. So lower sideband is inside, upper sideband is the outside. Okay. So when we have negative sign between this in phase and quadrature, it is the upper sideband, and when we have negative, that is a positive sign between in phase and quadrature part, so that is going to represent the lower sideband. So this is the S of t, that is the USB upper sideband. This is S of t, that is the LSB lower sideband. So these are the discussion about SSB-SC time domain and frequency domain representation. Next we'll see about generation and detection. Okay. So any doubt is there, you can write in the comment box. Please like, share, subscribe. Okay. Thank you. Thank you very much.